Yeah. And then the theme of this meeting is to like stop changing all the hardware. So a bit of both. All right, we'll give it till 3:02 for people to join up. Hello, welcome. Thanks for dropping in.
In the meantime, this is my setup right here, and I was just demoing the UI for the UX kind of prototypes are on that screen on the Raspberry Pi.
Get closer to that screen.
Yeah, here I'm gonna spotlight your video for a moment there, so you can get it on there.
Yeah, so that was Thomas's little prototype there that I just.
That's gorgeous. Can you zoom in on the UI there? I think that's something that a lot of folks haven't seen yet. That's looking alive.
Yeah, it's not live. It's just a mock-up.
Oh, nobody needs to know that.
Yeah.
You can step through and provide feedback on the UX and the click-through demo on some channel. What was it called?
I think it's a UX feedback or
UX design feedback. Yeah.
Yep.
There we go.
Okay, I'm going to grab the spotlight video again here back onto the bench, and let's go ahead and get started. Yeah, I just want to start off this meeting by saying, actually, first I want to start off this meeting by saying that this is recorded, just so that everyone knows. Your face and the video may show up on the website at some point to share with people what we've been doing, and also for team members who couldn't be here so that they can get caught up. Okay, now, to start off the meeting, I want to say that there's been an enormous amount of work, just incredible progress by all the teams. Everyone's been pulling late nights and long hours and exploring every avenue to getting us through to this thing, and it's pretty incredible. This is a ventilator usually takes 5 to 6 years to get designed and built, and we're trying to do it in like 6 months. So this is absolutely incredible work, and just a big heart and a lot of gratitude out to everyone who's been pulling for us. This is an incredible team to work on. So yeah, round of applause for everyone. So one of the things about having so much work going on in parallel and so much progress is it feels like it's hard to keep up with everything, and that's because it absolutely is, that a lot of things are changing at once. And one of the things we've been getting a lot of feedback on and hearing from a lot of the teams is that it feels like it's chasing a moving target. So as everything keeps changing, as we're trying to write hardware that works with software and software that works with hardware and UIs that work with everything and user manuals and documentation and things, it can be difficult to make progress on the work when everything is changing around you. So part of the purpose of doing this hardware walkthrough is to identify the things that we can lock down and say, like, this is what it's going to be for the current push. And the current push right now is the Covent demo that's coming up in just 2 weeks, 14 days. On the 18th of June, we have the Covent demo, which is, it's a demo for sponsorship. It's a demo for publicity. It's a demo to get support. We have our own internal schedules and things like that, but being able to participate in this demo does potentially open a lot of doors for us, both for financial and expertise to help with the project. So we really do want to build something good for this and demonstrate as much as we can. And so for this next 2 weeks, what we're going to try to do here is we're going to walk through the hardware setup here, go through piece by piece so that everyone has an idea of what's going to be in that demo for the June 18th demo. So so software knows what hardware they're working with. The mechanical and packaging team knows what parts need to go into the enclosure, and the hardware folks know what all the pieces are that fit together. So yeah, that's the purpose of this meeting, and we're going to try, for the things that we can lock down, we're going to try to say, like, these are the pieces that we're not going to change until after the June 18th demo, just so that people have a chance to build what they're building for that demo and have it work. There's, this is obviously not a complete ventilator. We know that there's a lot more work to do, but we're going to try to save hardware changes, upgrades, things like that. Anything that isn't sort of completely catastrophic to the demo, we're going to save until after June 18th. Yep. Any questions? Cool. Okay, we're gonna jump right to it. So we have the blower kind of as our first element. It's sort of been here since the beginning, and we've been designing around this blower for the time being. And I think that we can call this blower, the blower and the driver assembly, as fixed. So I've made these orange tags here, and we're just going to go ahead and mark off things that we feel like aren't going to change, and then we can write that all up later. So this is our ambient air source. So the ventilator being able to provide anything from ambient air to pure oxygen needs to have two sources of input gas. We have oxygen inlet here, and then we take ambient air from the environment. So this here is the oxygen input section. We have here a regulator that takes whatever unregulated oxygen tank input and brings it down to 10 psi, which is the operating pressure of the proportional solenoid. Now this stuff here is pretty much prototype. I consider this part of the bench setup, the test setup, and that the real ventilator starts here. So if we assume that the ventilator takes a 10 psi oxygen input, then we can sort of start the ventilator right here. And we have been able to get the proportional solenoid demonstrated and working. We can do closed loop control on that. Whether this is the final solenoid and the flow rates and things like that are to be selected, and also what solenoids we can get in quantity is up for grabs. But for the next 2 weeks, for the time being, we have a few of these and they are working. So I'm willing to call that locked for the purposes of the demo. Okay, so oxygen comes in here. It feeds into a mixing branch right here, where it joins the feed pathway from the ambient air and then goes out to the rest of the ventilator. So we've got more parts here in the upstream. So let's actually start. We'll start here from the blower. The blower outputs to this 3/4 tubing, which is kind of what we've standardized as our general internal tubing, unless otherwise needed. So one of the things that needs a different size tubing is that this pinch valve is designed around a 5/8 outer diameter, 3/8 inner diameter soft rubber tubing, and the dynamics of this are dependent on the geometry of that tubing. So what we'll do is we'll do a step down from our 3/4 tubing here. We have an adapter, and of course all of these things will be clamped. So we have these plastic clamps here, which I think is, if there's no objection, these clamps are what we're going to use in the final design, or in the demo design. So I'll just mark that off as one that we can see. How about mark it off as representative for all of these clamps. We do a step down, takes us down to that 3/8 inner diameter for the pinch valve. Again, unless we run into anything catastrophic, let's call these clamps selected for the time being. And it goes through this pinch valve that Mark designed. Excellent job, Mark, by the way, if we have you here on the call. The pinch valve provides a proportional control for the blower. So the blower, the inertia of the blower and the time it takes for the blower to spin up and spin down is longer than the fastest breath that we expect to be generating from the ventilator. So in order to get the response time that we need something that can move faster than the blower can change speed. So downstream from the blower, this pinch valve serves that purpose. It's driven by these commonly available stepper motors. You can find these all over the world. The 3D printed part here is a custom part. It can also be injection molded or machined. So this is, for the time being, this has worked really well, and we're going to go ahead and go with that for the demo. Continuing on with the 5/8 outer diameter hose, We go to the mixing T. So this is essentially just a T-junction where the oxygen, which comes from the proportional solenoid, combines with the ambient air that's brought in by the blower and controlled by the pinch valve here. Now, this part of the design is still pretty new, and I think that, for example, this is just clamped in there. It's just a fitting that's been clamped in there. So this isn't, this part still needs some work. So I think that's up to the hardware team that we need to figure this out and give an answer to everyone about what this is going to look like. But for the purposes of pneumatics and control, so from the software controller standpoint, this will all essentially operate the same as long as there is some place where the pressurized oxygen feed meets the ambient air feed downstream of the pinch valve here. So this is still a little bit in flux, and we'll figure that out as we finish up the next 2 weeks of work. The hose outputs here, we do another step up, so a change of diameter to meet our 3/4 inner diameter standard tubing that we're using for the ventilator internal pneumatics. And then we go through these venturis that were designed by Ethan. These venturis, they act as our flow sensors. They convert a flow to a differential pressure, which can be read by these differential pressure sensors. And the reason we do it this way, that we've pursued this design, is that these sensors are very easy to get. These are automotive sensors. Differential pressure sensors can be purchased in large quantities at low prices around the world. Some of the more specialized sensors that are created specifically for medical devices, such as ventilators, some of these are anywhere from $35 to $220 a piece. And more importantly, they're hard to source in a lot of places in the world. Even in the US, it's hard to get more than a few of them at a time, especially right now. So if at all possible, we're going to try to stick to doing some kind of a differential pressure sensing, and the Venturi is what allows us to do this. Again, this is a 3D printed part for now, but it is designed such that it could be injection molded in large quantities, again, at low cost. So there are some issues that we still have with trying to make this system work as accurately as we would like it to be, right? As we are using non-medical quality devices to try and provide a medical quality outcome. There's a lot of work to be done here, but for the purposes of the Covent challenge and the demo that we're trying to hit in the next couple of weeks, we should focus on making this system work. And then after the 18th, we can work on any sort of possible hardware changes that might improve the accuracy, or we'll find a resolution that allows us to use the current hardware to achieve the accuracy that we desire. So I'm going to go ahead and mark this off as these are not changing for the time being. This then leads out to our patient adapters. So these are the fittings that connect to the 22mm standard patient tubing. This is, from this point onwards, is hospital supplied hardware. So this is sort of our interface to the outside world. This is where the ventilator ends. It goes out to the patient tubing. It goes to a patient T. There's either a mask if we're doing, or a cannula if we're doing high flow nasal cannula, or an endotracheal tube if we're an intubated patient. Then that comes back from that T. Let me see if I can actually grab a T. It's probably worth showing people what this looks like, just so that everyone's on the same page with what is actually connected to our vent. So if I can grab, if this takes more than a couple seconds, we'll save it for later. So essentially what we have is we have the hoses. This is the patient tubing. Patient tubing connects to each of these ends. What I have right here are threaded adapters, but we actually have designed 3D printed parts that will go here. So these ones are stand-ins. This is not actually what we'll have for the demo. Tubing comes in here. It plugs in. This tubing then goes to a Y here. So inlet air comes in here. It goes to the endotracheal tube, which is delivered to the patient's lungs, and then returns here on the expiratory limb. There are no check valves in here. This is just an open flow circuit. And then another piece of hospital supplied equipment is there will probably be a inline humidifier as well, which works with all that standardized tubing to provide humidity and warmth to the air so that you don't end up drying out the patient's lungs. That's not part of the scope of our project. So at this point, we're not going to be designing any of that. So we can leave that outside the ventilator, but it's just good to know that it's there. So returning from the patient, the exhaled air will come here through another one of these patient fittings, through a, again, the 3/4 inner diameter tubing, which is clamped, and coming here to another one of these venturis. This venturi is identical to the other one, as it will see essentially the same flows going in and out of the patient. This is being measured again by these differential pressure sensors on the circuit board. And one difference here is that we also tap off the patient pressure sensor. So in the exhaled limb, we will measure the pressure that we're delivering to the patient as well. So there's a Y here, which then goes to the patient pressure sensor, which is here on the circuit board. Exiting the venturi, downstream of the venturi, we have another adapter, which brings us back to this 3/8 inner diameter tubing, which allows us to go through the exhale pinch valve. This is the same pinch valve. It's exactly the same design as the one in the inhale leg. And this pinch valve allows us to control the back pressure of the exhale from the patient, which is what allows us to deliver a controlled PEEP post and expiratory pressure. It's a minimum pressure that we maintain in the patient's lungs to keep the alveoli from collapsing, and it's an important feature of the ventilator, something for us to provide. Elizabeth asks, is there a reason why we are measuring patient pressure on the exhale rather than the inhale side? And the answer is there's no specific reason for doing that. It's a place to tap off the pressure. It could just as well be on either of these, and there will be a bias between them based on the resistance of the loop. So this is something that we will have to measure and compensate for in the final design. But for the purposes of the demo, as long as we have something that the controller is able to maintain control of the patient's pressure, it will work. The reason we don't tap off of this inlet here is that when you have a venturi, there's a drop in pressure across the venturi, right? And the venturi works by creating a vacuum on one side of the differential pressure sensing that is dependent on flow. So there's a constriction in the venturi. I know a lot of you know how venturis work. I'll just go over it quickly for those who aren't familiar with it. There's a constriction. The air accelerates as it passes through the constriction, which creates a vacuum in the line. And so because of this constriction, there's a pressure drop also across the venturi. So this pressure here is slightly higher than this pressure here, and this is the side that the patient sees. Now on this side, this is the source pressure tap off, right, which is being compared to the venturi vacuum. So because there's this drop here, and because of the venturi effect creating the flow dependent vacuum on this port here, neither of these pressure sensing points is at the patient's pressure, which is out here. This one because there's a vacuum created by the venturi, and this one because it's upstream of that restriction. So the pressure here that's being sensed by this line, it's sensing the pressure essentially in this limb and not in this limb, which is going to the patient. You get the reverse of that here on the exhale side, in that the venturi, the vacuum port, is now on this side, which is on the ventilator side, and the reference pressure sensing is on the patient side. And because the reference pressure sensing is on the patient side, this is the more accurate place to tap off the patient pressure. Now, we could just put another port here, right? That would do the same thing, or we could put a port here. But if we're going to use one of the existing ports in the Venturi, this is really the only one that we can use. I'll go ahead and mark this Venturi also as being locked in the design for now. Elizabeth also asks, are we including filters in the build for the Covent demo, either inline viral filters downstream or integrated HEPA filter? I think it would be good to show that. That's not in the demo here, but I think we should absolutely do it. And if we have the hardware, which I believe we have, we should absolutely show it to demonstrate that we understand the requirement for having filters. So good point. Thank you, Elizabeth. Yep. Moving on downstream from the exhale, Venturi flow sensing, we take that step down. We come in through here to the pinch valve, which we just talked about. So that one as well is fixed. And exactly as Elizabeth mentioned, there will then be a filter on the outlet side to prevent contamination. That is the end of the pneumatic loop. The electronics here we should also discuss. So we built this circuit board. This is our custom circuit board for the prototype. It's not, of course, the final circuit board that we expect to have in the ventilator, but it's meant to give us most, if not all, of the capability we need to get through this demo. So the circuit board is what we're going to be using for the demo. Kip is currently working on updating the circuit board for something that's more like the final ventilator, bringing all of the circuitry onto the board and adding the features that we need. But for now, this board has enough capability. It can control all of our actuators. It has sensors. We're going to use this one for the Covent demo. So what's on this board is the main board, which contains the power supplies. It contains the interfaces for the sensors. It contains the pressure sensors themselves. And it has sockets for both the Raspberry Pi, which is not plugged in right now, and the cycle controller, which is an STM32 dev board, which just plugs right in. On top of that, we have stacked 2 servo drives, one each for each of the servos. So these are PowerStep 01 drives. We have some of our setups are being built as well with L6740 drives, which are similar to these, but a slightly smaller power, lower power and smaller package. They're both mostly interchangeable. They speak the same control language. So being able to use either of these will work for Covent. But since this is what we have right now on the bench, we'll just go ahead and develop for this. So we'll keep these stepper drivers for now. I know that's a little bit of a confusion for people who got different stepper drivers, but we'll try to make sure that everyone has the hardware that they need to test. But for now, we'll run off of these, and if that changes, we'll let folks know. Yeah, there's a power supply that's not pictured here, but essentially we're just taking a 12-volt input, and for the purposes of the demo coming up, we are not going to change that. Martin asks, should there be a check valve just downstream of the blower to prevent oxygen backflow? Yeah, that is something that we had earlier in the pneumatic design and is not represented here. The reason being is that we've had some trouble with the cracking pressure and the chattering of the check valve. We haven't yet found a check valve that seems to meet our needs. So we've removed the check valve for now. And what we're hoping to rely on is the differential pressure across the pinch valve. So keeping the blower on at full throttle all the time means that as long as the pinch valve is at least somewhat closed, there's going to be a differential pressure across here, and that the pressure going out to the patient will be the smaller of those pressures. So we expect the flow to go only in that direction. Now that's something we have to verify, but for now, that is the plan. Yep. And speaking of oxygen, there is one thing that we're going to try to add if we have time. And this is not something that we know that we're going to have, but if possible, we would like to add an oxygen sensor in the branch going out to the patient. So what will happen is that a electrochemical cell will be added here and then interface electronics to allow it to be read by the ventilator mainboard, probably through one of these I2C ports. But that is something that we'll have to see if we have time to do that, because the next couple of weeks are going to be pretty busy, I expect, for us. David replies, I think that's a bad plan, as a response to the oxygen check valve. He says, I think that's a bad plan because if the pinch valve fails, it fails open and you'll flow oxygen back to the blower. Yeah, Elizabeth seconds that as well. Yep, so it sounds like we want to have a check valve there, and I'll leave that up to the hardware team to find a check valve. I think that doesn't seem to be a reason to force it to not be included if we can find one that works. And Elizabeth replies back, doesn't mean we have to include it in the demo though, which, yes, exactly. That's pretty prescient. Thanks, Elizabeth. That part of the reason for locking these things down is not because we expect that this to be the final design of the ventilator, but because we want to have hardware that people can develop on to get us to the demo, so that we're not pulling the rug out from under our software people all the time. Yep. And yeah, Martin writes, why is oxygen backflow a problem? And Tijani writes back, it's a fire hazard, right? So these components here are not certified as oxygen safe, and limiting the number of components in the design that will see pressurized or pure oxygen will make it easier to certify the entire ventilator for operating with oxygen. We don't know that the blower is a fire risk, but we also don't have a clear pathway to certifying that it isn't, which makes it a challenge. We saw an article like a month ago that a ventilator fire burned down a COVID ward in Russia. So it does happen. Electrical fires and fires in hospitals, especially where there's oxygen, is a risk, and it's something we're going to need to think about, us and the manufacturers who will eventually be building the ventilator. But for now, to demonstrate that we have something that works is a little bit different, but we still have to keep that in mind so that we don't design ourselves into a corner. Yeah, basically, David says getting an O2 safe blower was a challenge. Doesn't mean it can't be done, but it's simpler to avoid it if it's easy. And cost does become a factor, says Neil, and also availability, right? So we've been trying to get one of these oxygen safe blowers. It took us a month, and we were able to get one, and we only were able to get it on eBay. And the blower that we also sourced a blower from Moog as well that was that even then wasn't oxygen safe, and it cost more than everything that's on this board. So it's a challenge. Yep, that's the walkthrough for now. Thank you for all the questions that people have been submitting on the group chat. I want to open it up to any other questions, either in the chat or on the call, so that we can just get everyone. All questions are welcome. Nothing's too small or too big.
So I guess a big one from hardware, and especially as we go into putting this design together for beta, is do we have, I know that there's kind of a running list of materials on Google Drive. Do we have, or are we going to be working on making a more concrete one, or with a little bit more thoughts into what's finalized and what's not? I like the sticky idea, so maybe something like that, because I guess that's been something that's been kind of difficult, for me to go through and start putting parts together when I'm not really sure what's being experimented with and what's been chucked.
Yeah, real quick, who's speaking there? I'm not seeing the whole.
Oh, that's
grid.
Tijani.
Okay, yeah, thank you. Great, sounds like you were speaking to that.
Oh, I was just gonna say, are you familiar with the system design GitHub repo and the bombs located within that?
I am not. I'm kind of trying to learn GitHub.
No worries at all. I can link that in the chat, but
yeah, that'd be huge.
Edwin, correct me if I'm wrong, but I think that's the most up-to-date place where there's a ton of specs around which parts to buy, alternates, and links to sources where you can buy them from. So
yeah, I'm just
absolutely.
thinking more from yeah, go ahead.
I was going to say, like, I think we should turn that over to Martin, who's been doing the documentation, if you want to speak to that.
Yeah, and Grace as well, because she's also been doing this. So there, some of that is still in flux, as everything is. But I think yes, the most up to date one is there on the GitHub repo, and you don't really need to know GitHub to read it. It's reads very much like a website that you can browse around and look around. And I think we've done a pretty good job of cross-linking everything. But if you have trouble finding something, let us know, and we'll try and update it. Some of the things are still in question, and I think we've tried to mark the ones that are uncertain. And some of it still reflects the fact that we have not decided on the inner diameter of the tubing. But I think we may have even updated that to say that it's 3/4 now. So most of that info is there, except for the oxygen part. So I think that still some uncertainty on some of the oxygen limb parts.
Yep, one of the priorities as we get that figured out is to make sure that that goes over to your documentation, Grace and Martin.
Yeah, and also if you do try and put this together, also try and reach out to me, because I have lots of additional parts, lots of tubing and adapters and stuff. When you order from McMaster, it comes in 10s or 20s. And if I'm only building 1 or 2 or 3 prototypes, I still have leftovers. So whatever you try to build, talk to me, and I'll let you know the easiest way to proceed.
Well, I'm actually doing the model, the solid model. So I'm just looking to make sure that I have the most up-to-date kind of dimensions and parts and things like that for when I do like fit integration, things like that.
Yep, yeah, and we'll make sure that you have that. That's really important.
Cool.
One thing that bears repeating again is that like the purpose of doing this walkthrough is to make sure that we get all of these part numbers and physical configurations captured, so that the software and the hardware design stay in sync. And one of the really big reasons for trying to lock down this hardware is so that software has something that is stable, that they can design against, and that they can test their software on, that isn't always changing. And Martin, we might have just lost Martin for a second there, but Martin has also been working on, oh, there he is. Yeah, one of the reasons for doing this is to have a stable hardware setup for software to test on, and Martin has been doing that with the pizza farm. Do you want to speak to that really quick so that people know what resources are out there?
So right now, I have one prototype that's very much like the one that Edwin has, and I don't have a webcam to nicely aim this, but right there, it's still the wrong diameter tubing, but I think by later today I'll have it switch over to 3/4 because I just got the new Venturis from Ethan. And so this prototype is now hooked up to a machine that's open out to the internet. And there's, I think, 2 people now that have SSH access, and they can push the code to this device, flash the controller, and it will do stuff. I should also get a webcam soon, so you'll be able to even watch it do stuff. And we will attach sensors to various parts of it, so you could actually even get data when you do stuff. So the goal will be, I think I should have a second prototype soon. Tom and Hugh have sent me their PCBs. So at some point, I think there will be one prototype that will run tests on software. Whenever software changes, any change in the software that tries to, like, that we think we will merge to the main branch of the software, like what will be the definitive latest version, we'll have to run tests against the real article here. So every time someone has a significant software change, it will automatically, that updating that software on GitHub, the code will be noticed by our system here, and the server will pull in the latest code and will automatically deploy it to the device and take a whole bunch of readings and report on whether it's still behaving as expected. So the sophistication of those tests is still in question. We'll start with something really simple. You know, does the blower blow? Do the pinch valves work, and so on. and then we'll ramp up to some more significant tests of the loop and everything. If I have multiple items, if I have multiple prototypes, probably someone will be able to just experiment on one remotely and kind of in a free kind of sandbox mode kind of thing. So that's the plan. I disappeared for a second because I was gonna show you some alternative adapt to that T adapter that was not decided, but I'll check in with you in a few minutes once I find the parts.
Cool. Yeah, that is still very much in development. So whatever we can do to try and lock that down is going to be good for everybody. There's another parallel effort that I want to make sure I don't leave out is that John Bette from Modelon and David Gearson and others have been working on a software simulator as well so that we can test our control algorithms in software alongside a software simulator of a human lung and a human that is providing lung effort as well. So we're developing a set of tools so that we can anyone who's working on the design of this thing can test out what they're working on either in software or in hardware. So just check the chat here. If unless there are any other questions on hardware, I want to turn it over to Tijani to go over the work that he's doing on the 3D model.
All right, let me get set up here.
So I'm going to go ahead and release the video there. So go ahead. Yep, got your screen share here.
Yep. So this is kind of a collab between Randall and I, so he might be able to speak more to the enclosure than I can. I'm kind of in the process of essentially trying to figure out how to take that schematic and these parts and figure out if it fits and where it fits and how interfaces look. In my infinite wisdom, I put parts together right before this call and realized that this config that I have here isn't going to work because this tube doesn't go over there very well. But yeah, so essentially what we're working on here is trying to figure out how we can get all this stuff to fit in a nice package. Because I guess for alpha, there's a lot of tubes crossing over each other and a lot of kind of things that when we go to streamline a design, the way that you have it on the table, Edwin, looks really nice and compact. And so that's kind of what we're shooting for here. And so I guess I was talking to Elizabeth a little bit about this, but this will be a good chance for us to nail down things that we don't have, like fasteners and zip ties or basically components that aren't, stuff that you guys have been worrying about a bunch, but we're going to need to start speccing out. So that'll be a good source for kind of a secondary BOM. I can start coming up with lists of things like that. The concept that I'm kind of working with here is I like the idea of having a one mounting point for all of the plumbing or all the pneumatics. And so it's kind of broken up into, we have a faceplate, which will contain the display. And I'm toying with the idea of also putting the circuit board somehow mounted to this assembly. I'm going to figure out if I can make that work. And then we have all the filters kind of on another piece of acrylic so that this is going to be very modular. And I think, Ethan, you were talking about how you guys really want to have this thing mount from the front. So that's something we're working on here, is making it kind of modular and attached to the front plate, or as much as we can to the front plate.
Yeah, I mean, I think just the experience of building it was like making all of the connections was really useful if you could kind of get arms in from multiple sides and really kind of see everything coming in. It was really nice the way that was built. We could like turn it on its face and basically just like spin it around 360 degrees.
Yeah.
But then where it was annoying was like having stuff mounted top and bottom of the shelf and like wires having to like route through a bunch of stuff to get. Obviously having the PCB helps with that a lot. Yeah, I think this looks really cool.
Yeah, I think my idea is basically I want to try to see, that's why I was asking about parts, because I want to make sure I have every part's dimension right, because it's pretty obvious that some things like, if we can nail down the size of this box here and things like that are kind of important, but I want to have everything kind of mount to a plate if we can. So this acrylic here will kind of be the home for all the plumbing, and all it needs to do is then plug into its respective ports. And that way I think it'll be really easy for you guys to, Randall has designed this so the whole back will come off, so you can lift this whole sheet out and, like a cookie sheet, put everything you want on it and slide it in if you need to change out a component, as opposed to like, reaching your hand in under here and trying to make a connection.
Something that might be useful, just a thought that I had was, if the front plate where all the filters are mounted is also mounted to this acrylic shelf, and that the whole thing slides in and then bolts to the front, then you can build the entire assembly outside of the vent and then just slide the whole thing in and then
make wiring connections.
Yeah, I don't see why we couldn't do that.
Yeah, because I was going to say making those connections to the filter housings actually would be pretty annoying.
Yeah.
Like the tube, think about like one thing that was definitely a learning experience for me from the alpha build, and we sort of got everything to work, but like if you don't have a straight lead in for a tube to go onto a hole, like it can like look great, right? Two components that are like attached really close to each other, having a nice short piece of tube, but that's actually really hard to assemble because you have to like compress the whole assembly and then attach everything. Unless you do that all out of the box, which I think we just like maybe could have done. So it's just a thought that like to think about how tubing gets assembled and how adapters get put in. Yeah,
that's a good point. I don't see a reason why we couldn't just throw some supports here and maybe a bracket and then have this whole thing to go together. Yeah, that's actually a pretty good idea because the way that this is right now isn't that intuitive because I guess this plate has to come in from this side because it mounts on the inside. So that means you'd have to put the tube in and then make the connections and slide this in right now. So that's a good idea.
Yeah, and there's also some type of snap fittings that we could use rather than having to like reach in there and mount that front acrylic plate, putting nuts on the backside of those studs. So there's other options there that we could come up with.
Yeah.
Yeah.
Or maybe it doesn't need to bolt at all. It just kind of, locks into place. We don't really need a gasket there or anything, or need to be sealed. So
yeah, that was kind of my thought is. Yeah, no, go ahead.
No, I was gonna say it could just rest there. So we could have brackets on the sides that this whole thing just kind of like snaps to or mounts to, and then just, a couple screws to hold it in.
Yeah, that was kind of my thought with, and I think I'm probably going to get rid of these supports here, but yeah, like this thing is basically going to need, because it doesn't need to be, this thing doesn't need to be bomb proof. It just needs to be secure. So yeah, if we put like maybe 2 tabs right here and drop a stud and a nut in there, or even just a snap fit or something, that means that this whole shelf, all the supports here, this doesn't need to bolt down to anything. So that would make it really easy because then you could literally slide it as opposed to worrying about making connections or fastening things.
Yeah, the thing that just occurs to me now is actually if you had those tabs be on the back plate, that when you bolt the back plate on, if you had, little feet, I don't know if you can see my hands or see my image, but like had, something on the back plate that holds that acrylic place in. So it is actually just sort of sitting there until you mount the back plate. And then the bolts that hold the back plate on also hold that sheet down.
Yeah.
Very cool.
Edwin, have you spec a fan for blowing into over top of the boards?
No, but we can choose one quickly.
I mean, there's like choose any even number millimeter of hole spacing, and we'll find a fan that it works. Like the cooling requirements aren't overwhelming.
That vent is for a 60 millimeter fan, 12 volt, probably 24 volt as well. I don't know what you guys are running. 12
right now. But that means that pretty much any computer fan will work. So
exactly.
Probably 90 millimeter square box fan with a grill.
Okay.
If you want part numbers, we'll make that happen.
I guess to address Neil's concern about the shock and vibration testing, what's our acceptance criteria there? Because I guess, obviously we don't want, like I said, I don't want anything loose. So I want this thing to not be, I don't want to be able to shake it and hear parts rattling around. Do you think that that's something that, like, I guess that simply restraining it the way that we were talking about, it wouldn't pass that? Or I guess I'm just trying to gauge how vigorous these tests are.
So the tests I'm looking at, they have peak accelerations from 15 to 30 Gs for shocks on each axis.
30 Gs.
And
where are these specifications?
80601 212.
Wow.
There's a shock test. It's like 15 to 30 Gs for like 12 or 6 milliseconds. And then there's a vibe test going up to 500 hertz for 10 minutes per axis. And the acceptance criteria is usually basic safety and essential performance are not compromised. So that means, nothing happens to the device that compromises the usage of this device, and nothing compromises its effectiveness at continuing to perform. What I still need to look at is whether those tests are done while the device is on or not, and I'm pretty sure it's done during, I think it's not done during operation.
Yeah, thanks for sharing that, because that might change my decision a little bit, because I guess like the vibration test I'm not too worried about, but the shock, 30 Gs is a lot. And especially with connections that, I'd hope that our tubing connections are pretty.
Yeah, I wouldn't worry about the tubing connections.
Yeah, but I'd be worried about if we moved something enough that a wire got pinched or something fell out, that would be a problem.
Yeah, it probably means that we just want to make sure that everything is secure, that we don't have something that flops, right? 30 G should not be too much shock to handle if everything is bolted down and we don't have anything super fragile.
I would think the biggest thing that really gets to is mounting the servo drives.
Yeah.
Yeah, if it's in the wrong axis, it could cause them to skip, perhaps.
Or I'm just thinking more about the fact that they're like the largest, densest piece of mass in there.
Yep. And what you're talking about specifically are the motors, right? The big cubic things.
Yeah.
So then it probably makes sense then to make sure that those are mounted to the frame, as opposed to this kind of thing where it's mounted to a flexible piece of plastic and a sort of flexible piece of metal. Yeah. So that might be something I'll just consider doing that with my design, is making sure that it goes straight to the body itself.
Yeah, Tijani, this looks really, really good. And one of the things we've been trying to do for the Covent challenge is to properly scope the objectives for this demo. Like if we try to build the entire ventilator in the next 2 weeks, that's almost guaranteed that we won't be able to do it, right? So one of the things is trying to select objectives that are reasonable, that we think we can hit without killing ourselves, to demonstrate as much forethought and as much progress as we can to Covent. So along those lines, how much of this do you think we could build in the next 2 weeks? Even if it's just a physical demo.
Physical demo or a digital demo?
Yeah, so what I mean to say is, like, for functional demo, right now what we're committing to as a minimum demonstration is this tabletop build that I just showed everyone, that this will do the pressure control and it will be hooked up to all of Covent's instruments, and we'll do pressure cycling and we'll get data from that setup. But if at the same time we have a physical model built up similar to what Tijani has just shown us, I think that would be very impressive for Covent. And I don't want to like push us too hard too fast. Again, like the real goal is to make a ventilator, not just to please Covent, but that would be pretty cool.
I mean, Edwin, just a thought on that. Like before we did the alpha build, we had the box and the faceplate and the screen, and I threw all of the components in the box and turned it on its side. And it looked pretty good. So like, I think we can get to there pretty fast, and then getting, something more than that. Like, I think we should just see where we go.
Yeah. I want to stress that it doesn't necessarily need to work, right? Like it doesn't need to be able to plug into a test lung and do cycles. If we do get to that point, that's awesome. But even just having it visually to show that we've thought about how this thing is going to be packaged and how it will actually appear like in the field goes a really long way to getting people to take us seriously. And the more people take us seriously, the more help we get from professionals. So and people in the field. Yeah, I mean, and the more serious we are, yes.
Just from like a looking at a point of view, I mean, I might defer this more to Randall because he did the whole enclosure, so he might be able to speak a little bit more to this. But it does, like, if you looked at it, if you forget that it's open in the back and there's nothing in there, this looks really good, kind of thing. So like, if we want to be taken, seriously and look good, it might actually be good to have the enclosure. We shouldn't prioritize it over having the internals in there, because anyone that actually cares is going to look in the back and look at the parts. But if we want to be taken seriously beyond like, okay, this is our alpha build in a tub, it might just be good then to try to go full send on the actual enclosure and look like an actual proper ventilator, if that's possible. I don't know if that fits anywhere in our scope of work. And I know that Randall and I were talking, he's looking at, I think you said you were going to try to do a few more iterations of this or something like that.
Yeah, I was going to try, just based on Ethan's feedback and Elizabeth's, just trying to get the clamshell to be the top, the rear and the sides of the enclosure, and just having that front be kind of open and accessible to mount everything. It's a structural issue, and I just need to figure out how to overcome that.
I think if it's like what if it's like what Tajani was saying, maybe we get around that. Like if everything mounts to a plate that does, insert, maybe that's okay.
Yeah. Okay.
Yeah.
But getting it built, might be the hardest thing.
So as a proposition for the next 2 weeks kind of deliverable, I would suggest or propose that we try to have a design complete in CAD and cut the acrylic pieces exactly as we'd like to assemble them, and then build like a plywood fixture that we can bolt the acrylic pieces to that is like a stand-in for the metal enclosure, because I don't think we're going to be able to make and get right the metal enclosure in the next 2 weeks, but we easily could get the acrylic pieces if they're just laser cut, because we have the ability to iterate on that like locally pretty quickly. Does that seem at all feasible?
Elizabeth, like how can Seaport cut and bend this? You just don't think it'll fit? I have a grinder.
They definitely can cut it. I think they can bend it. If not, I know another person that can bend it. I just because it involves multiple out of our wheelhouse people, I just doubt that we're going to get it right and all integrated and assembled in the next 2 weeks.
What are those shelf supports made of?
That was just, I guess I designed it to just be sheet metal. But now that I'm kind of reevaluating, I may just do acrylic and kind of just do corner fasteners.
I'll +1 corner fasteners over Elizabeth's puzzles. No, I don't know.
Is this something that a contract manufacturer could build for us if we send some drawings out?
I mean, I think it's worth. I guess Elizabeth, what's your estimate on what it would take to get this prototype? Not asking someone to volunteer. Or Randall or Tajani.
I mean, it's reasonable to do in a couple weeks. Like, if our design was complete today, I think we could reasonably build it in the next 2 weeks. But our design is not going to be complete today, and it's not even going to be complete in the next 1 week, probably. So I don't think the fabrication is necessarily the bottleneck, but I just don't think it's realistic to try to get the entire package thing assembled in the next 2 weeks.
Yeah, I mean, because if we could probably send this to a manufacturer right now, and they could knock it out in 3 or 4 days if they were willing to. But they have backlog, and it probably take at least a week, maybe 2. But then we don't know all the fasteners that we need here. We don't need know where all the supports are going to go. So it wouldn't be final, and it would just be a cost that we would kind of waste, because we would have something that wouldn't really do everything that we need it to do.
Yeah.
Yeah, and I mean, one of the things we could do is if we just laser cut each of the sides as flat pieces out of acrylic or some kind of plastic, we could just put it all together to show what it would physically look like, but say that, hey, we expect this thing to be in the final folded sheet metal thing. Really quick, before we move on, I wanted to check and see if Hari is on this call, because Hari requested to present a control design that he wanted us to look at today during the meeting. So Hari, if you're here, if you want to take that up, otherwise it is posted in the engineering channel, and everyone can go take a look at his oxygen mixing control design that he posted earlier. But he did make a request to present to this meeting. I don't see Hari in here, so going back to this, I think that whatever we can build would be great to show. I also have some resources at rapid prototyping places that build these kind of things, that if we sent them a drawing, even if it's just a rendering like this, and just say, hey, do you have the bandwidth to help us build this thing? They might be able to do it. So if you want me to contact one of my contacts and just be like, look, this thing is not final. It doesn't have all the drawings and not every piece is in there. But if you want to make a folded thing for us to show, we'd really appreciate it. And they might be able to do it.
Yeah, because one thing I was thinking is that, we could just, if it's just sheet metal and if we want to take a risk, this is definitely a risk. So we could say we don't want to do this, but you know, if we took this enclosure right now and we said, all right, well, we know we're going to have to put, you know, some fasteners and some adapting stuff, we could, you know, it's sheet metal, so we could go punch these holes ourselves. I know that's not ideal because that's kind of gambling on something not being a problem. Like,
yeah,
we could send this out now.
My question is how much is it worth it to us for the sake of appearances for the Covent deadline versus like doing things out of sequence with a design that's not really ready to be prototyped? Like, in my mind, yes, it's important to like do well in this challenge, but it's like not at the risk of spending our attention on stuff that is like out of sequence with our actual level of maturity.
Yeah, that's why I'm saying let's get someone else to do it. Like, I think it would make sense.
Communicate a fair amount.
If we can lever outside resources to do this that aren't currently working on other things for us, that would be best. A few of us have a call with Covent in 2 minutes, so I think myself and Ethan, we're going to have to drop off the call. But if there's more hardware stuff to discuss, I'd be happy to designate someone else as the host to continue the conversation. How are you guys doing? I think we're going to have to run. So
I'm going to run with you really quick though. If we do need someone else to prototype, Neil, I know I completely missed the call with Citrus, but I know that was mostly with the respiratory therapist, but this is something we could also ask Citrus's engineering group to maybe have a stab at and see if it's something they could turn around. I don't know.
Super. Yeah, let's keep that conversation open. We're going to have to run, but thank you everyone on this call. And the next 2 weeks are going to be really exciting. And whew, all right, let's go do this thing. This is amazing.
Edwin, it incredibly excites me to hear you that excited after the number of times I've seen you post things right before I get up.
Yeah, there aren't many other things that are worth staying till 5 a.m. to do, but I think this is one of them. So let's do it.
Awesome.
All right, we'll see you guys. This will be recorded. It'll be posted up for people to review and folks who missed the call to catch up. All right, let's go. Thanks, guys.
Cool.